Okay, welcome Bradley, Ralph, and Jordan, and Victor, and Caesar, and I'm sure there'll be more coming in. This is the kind of middle of week 2, so we're getting through it, and hopefully it's going okay. I know it's not an easy class. I'm never pretending that. It's not one of those. But it's something I'm here to help. You help each other, etc. In fact, it's really hard to find tutors because they're you. That's the problem. But I'm always here to help you out. So today, let me share my screen and I can show you what the plan is for the day. So the plan of the day is, as usual, I'll start out with any questions you might have about the homework or anything else. And then what we'll do, it's actually quite easy, but the idea is it's going to be exploratory. What I want you to do is I'm going to have you do stuff and kind of see what's going on, but I'm going to lead you through or walk you through the process of understanding. And we're going to be looking at what happens when you do a row operation on the identity. Okay, very easy, I promise. Okay, then what we'll do is we'll define what an elementary matrix is. And that's going to come right from what number 2 is doing. And then after that, we'll talk about what happens when you multiply an elementary matrix by any old matrix. And we'll see that actually it just is very revealing and very nice and helpful. Then we'll see what happens when you're looking at an elementary matrix, and you want to see how does that compare with what happens when you take an inverse of a matrix. So we'll look at elementary matrices and A inverse. And then after that, we'll look at, well, if you have a product of 2 matrices, A times B, and you look at RREF of A, is there, what kind of relationship happens? And we'll see that there's some relationship. And then we'll say, what are the dimensions of an invertible matrix? So for example, can you have a 5 by 7 matrix that's invertible? So if A is 5 by 7, is there a B such that AB is the identity and BA is the identity? And we'll see. We'll find out that there's special requirements for a matrix to be invertible. And then we're going to have the biggest theorem of the entire quarter, but we're just going to start on it. And that is TFAE. And we're going to have a following or equivalent theorem. And we're just going to have 2 things today. And that list is going to go on and on and on. It's like every week we're going to add a couple more. And by the end, we're going to have like a whole alphabet of lists. So of TFAE items. So that is the plan of the day. So let me open it up. Are there any questions about anything that you might have been working with?
Yeah, do you mind going over homework problem 39?
Okay, so just a minute. I think there's one section on this one, so I think I can get to it. Takes a moment to find it, you know how that is. So 39, that is 2.139, I think, right? Let me find it. Okay, so we want to find a formula for the 2 by 2 standard matrix, ABCD. Okay, for the inverse of that matrix, actually. So let me go ahead and pop that in. Copy and paste, but I don't know if that'll really work because there's stuff involved. But see what happens. And there it is. Just a second. Yeah, so it copied and pasted some of it. All right, so let me finish the rest of it because we're gonna need it anyway. So let's suppose A is your standard 2 by 2, and they made it easy by just saying it's ABCD. So let me go insert, symbol equation, good old matrix. Backspace 2 by 2. A, B, C, and D. Okay, now hopefully, if you were listening or reading the book, there's a step-by-step process to find an inverse. What's the first step?
Insert the identity matrix along with that.
Right, right. So we're going to write AI, basically. So let's do that. So now I'm going to take a 2x2 matrix, and I think I can just copy and paste it, and then add a couple columns. If I remember, that should work. Okay, so what numbers do I put right here?
1 0.
Good.
And then 0 1.
All right, so what we need to do next, okay, that's the first step. What's the second step?
RREF.
Yeah, we're going to RREF this matrix. And if you remember, the way you RREF a matrix is we need to get that first top right to be 1. Is that clear? So that's how you usually start. Now, I'm going to make an assumption, and that is that A is not 0. Okay, if A is 0, then what would be my first step?
Swap rows.
Yeah, I'd swap rows, and then I'd have to make the assumption that C is not 0. If A and C are both 0, what happens?
I don't think this will work.
Yeah, it's not invertible. Remember that not all matrices are invertible. Not be an example where you don't have an invertible matrix with A and C both being 0. So in particular, I'm going to assume A is not 0 just to make life a little easier. And I'm going to take that first row and do what to it?
Multiply it by 1 over A.
Good. So I have a 1, I have a B over A. And then I have a 1 over A. And 0 over A is still 0. Any questions on that? So far, so good? Yeah, this is basically busy work, but it's important busy work and it's good practice. Okay, so now I got that 1. I want to make sure to make it RREF. Below that 1 must be zeros, right? And there's only one row below it, so it's easy. What row operation do I do to make that C a 0?
Multiply row 1 by negative C. Add it to row 2.
Good. And when I do that, that C becomes a 0. That's the whole point. And then I'm going to take B over A times C. And then a negative B over A times C plus D. Okay. And is it okay if I do 2 steps at once? Not 2 linear algebra steps, but an algebra step. And that is do a common denominator. So negative BC over A plus D is the same as D minus BC all over A. DA minus BC all over A. All right. So I'll write it out, and then you'll see what I'm talking about. So we're going to have a AD minus BC over A. Did I lose you there, or do you follow the algebra? Is that okay? Okay, so then again, I've multiplied. So what I've done is I've multiplied it by negative C and subtract. So that 1 over A becomes negative C over A plus 0 is negative C over A. And then the 1 stays a 1 because 0 times anything plus 1 is just 1. Any questions on that? Totally clear so far? Okay, we're getting there. What's the next step?
We need to get that AD minus BC over A into a 1.
Right, and what row operation do we use?
Multiply the reciprocal of that.
Yep, going to multiply by A over AD minus BC. So let's do it. It's messy, but it's important. And this is more than just an exercise. This is actually an important, huge theorem in math, okay, that's used all the time. So obviously that AD minus BC over A becomes a 1. Okay, and by the way, we're making some assumptions, right? A is not 0, we've decided. And also AD minus BC must not be 0. Is that clear? Because if AD minus BC was 0, then we don't have an invertible matrix. And I'm just going to jot that down. That's the main one. So AD minus BC is not 0. Because if it was, this doesn't work. Is that clear? All right. Have you seen AD minus BC before in your life? This is famous. That's a hint. In one word.
Dot product.
Good try. But it's not the dot product, actually. It's another one that starts with a D.
The
Determinant.
It's the determinant. Yeah. When you do cross products and you do determinant, that's what you did, remember? So that AD minus BC, the determinant is non-zero, is essential. And that's actually the biggie right there. Okay, that's a huge, huge fact in our class. And we're going to get into that on Friday. That's not today's lecture, but it's Friday's lecture. Friday's all about determinants. But I figured I'd kind of give you a heads up since we're doing it right now. That way I can on Friday because I remember we did this. You know, I'll pretend that you don't remember. Okay, so we got that. And now so what we're doing is we're multiplying by AD minus BC over A. A over AD minus BC. And what we get is the A's cancel and the denominator becomes AD minus BC. Any questions on that? Easy enough? All right, we're getting there. Okay, what's the last step?
We need to multiply row 2 by negative B over A and add it to row 1 and store it in row 1.
Good, good. And I guess I should say the next step, not the last step, because there's actually another step. So we're going to multiply by negative B over A and add. So let's do that. So when we do that, let's copy and paste. So the bottom row stays the same. The top row, the 1 stays a 1. The B over A becomes a 0. That's the whole point, right? The 1 over A becomes I'm going to do a couple things. It becomes a 1 over A minus B over A. But, oops, over A. Any questions on that? Okay. But I can put that under a common denominator, right? And I get B, 1 minus B over A. Okay, and now the fourth number, that 0, we're multiplying again by negative B over A and adding, so we get negative B over A. Any questions on that?
I'm kind of confused how the 1 stayed the same while we transformed everything else on the top row.
Let me see if I made a mistake. Which one? I see a lot of ones.
The top left-hand corner one.
This guy right here?
Yeah.
Okay, so what I did is I took 0, multiplied it by negative 1 over A and added it to 1.
Oh, okay.
or negative b over a and add to 1. But 0 times anything is 0. Add to 1 is 1. Any questions on that? Any more questions? Okay. Now what we can do is we can do the very last step, which is write down the answer. And what is the answer?
The new 2x2 matrix that we just made.
Yep. I have to do it this way. That's better. So I need to find the inverse now. And the inverse, if you remember, the very last step I'm finding the inverse is the right-hand side. It's what's to the right of this left identity now. And that's that mess. Is it okay if I don't type it all? It'll take me a long time to type it. You okay with that? But it can be all typed out.
What do we do with that 1 since it's in terms of A, B, C, and D?
Which one?
The bottom right one in row 2.
This one right here?
Mm-hmm.
That's just a 1.
Okay.
Yeah, if you have a 1, it stays a 1. Unless it looks like I might have made a mistake somewhere, so I should probably double check. But so far, first step looks good. Second step looks fine. No, maybe it's all right. Okay. Because there's a nicer way of writing what the inverse is. Don't memorize this. Don't memorize.
I think I know where the mistake is.
Huh.
When we multiplied negative b over a to row 2 and add it to row 1, where did it go when it comes to negative c over ad minus bc? Do things cancel in that situation?
Which one? That one?
Yeah.
Okay, so we had negative c over a, right?
Mm-hmm.
And what we had done is we multiplied. No, that one's fine. We multiplied by the reciprocal.
Yeah.
We multiplied by the reciprocal, right?
Mm-hmm.
So the a's cancel when you multiply by the reciprocal. So that's correct. It might be correct. It's just there's cleaner ways of writing it. Let's just put it that way.
Okay, I'll go with it.
Any questions? The main thing is showing your steps. Because I have the reason why I'm a little concerned is I have this one memorized. It's that important, and it's a lot prettier. But there's some algebra to do, I think, and that's why. Any other questions on this? In fact, if you want, here's the true inverse. 1 over AD minus BC times D A negative B negative C.
Which is transpose, right?
No, that's just the inverse. That's the formula. That's the formula I have memorized.
But the dA negative C. Okay.
Yeah. And maybe it works with all this mess. But this is the way you'll want to memorize it. It's the 1 over the determinant times switch the diagonal and make the off diagonal negative. That's how I have it memorized. Any questions on that? Make total sense? Did I do anything tricky? No. And that's how this class is. There's no hard steps, but it's hard to know what step to do. Have you found that?
Yeah, for sure.
Did a little messy fraction work, but really, it's just basic algebra, isn't it? When you look at the steps, it's not like I'm using partial fractions or something. It's just very basic algebra, but it's really hard to know what algebra to do. That's what makes this class hard, because it's just linear algebra, not even squares. Any other questions?
Can we do 41?
Okay, 41, and I think I'll call it after that because I can only go do so many. So 41. Okay, so we let A equals 103, 234, 102. Find the inverse. Okay, if the inverse does not exist, explain why. So let's see if it 103, 234, 102. See if I can remember that. 103, 234, 102. Whoops. Backspace and then do it. One, 0, 3, 2, 3, 4, 1, 0, 2. Okay, so let me double check that that was it. Yep, good. My memory's not that terrible. Okay, so what's the first step? Just like we did before?
Put the identity matrix on the right.
Right, put the identity matrix on the right. And I'm going to do that by just inserting a bunch of columns. And one more. By the way, do you see why the exam is not going to be on computer typed out?
Yeah, that would be a
That'd be
nightmare.
rough.
Yeah, I mean, a lot of people think I'm mean, but I'm not that evil. I wouldn't do that to you. But you do need to know how to do this on paper, though, just a warning. So don't just watch me. I would recommend taking notes and writing it out. Does that make sense? Okay, and besides that, it's homework. So what do we put on the right? Put the identity, 1, 0, 0. 0, 1, 0. And 0, 0, 1. Okay, that was the first step. What's the next step?
RREF.
Yep. All right, so to RREF, the nice thing is that the top right, top left, I mean, already is a 1. So what can we do now?
Multiply -2 times row 1, add it to row 2 and store it there.
Yeah, so let me put it in kind of simpler words. We want everything below that pivot 1 to be a 0. So I am going to do 2 row operations in one shot because it's pretty safe to do that in this case. So what I'm going to do is I'm going to do what Bradley said, which is multiply row 1 by -2 and add. So I get a 0. We still have the 3. 3 times -2 plus 4 is -2. 1 times -2 plus 0 is -2. And then the others stay the same because we have zeros. Any questions on that row? Okay, now I'm going to take the first row, multiply by -1, and add it to the third row. And that 1 becomes a 0. The 0 stays a 0. The 2 becomes a -1. The 0 becomes a -1. And the 0, 1 stays 0, 1. Let me know if you're stuck in any place, because I don't know where it is that you got stuck on while you're asking this question. So you have to let me know. Any questions so far?
No.
Okay, here's the good news. Without doing anything more, how do I know this is invertible?
We don't have any zeros yet, and we're not going to get any.
Well, there are a lot of zeros in there.
I mean, at our pivot spots.
Yeah, so right. So more importantly, there's 3 pivots. Okay. So remember, you only need to REF to decide whether there is an inverse. You need to REF to find the inverse. Is that clear? Okay, so we need to REF to find the inverse. And the nice thing is I'm going to do things a little bit differently than you would kind of do in a computer. In a computer, the next step would be divide by 3, the second row, to make that a 1. Do you see that? Because you do in order, because computers care about order. I'm not doing it that way. Instead, I don't want fractions until I have to have fractions. Does that make sense? So what I'm going to do is I'm going to take the third row and multiply by -1. That's safe and easy. Do y'all agree?
Yeah.
But I don't want fractions, so there's no reason to make that 3 a 1 yet. Right? If you were programming a computer, you would make that 3 a 1 right away. You know, that would be the next step in the code, because computers don't care about fractions. They don't complain like I do. Maybe you don't complain either, but probably would. No reason to have more than you need. So I'm going to multiply by -1, the third row. Any questions on that? Okay, then. Now, again, I want to avoid the fractions as long as I can. So I'm going to use this 1 to make what's above it a 0. Then I still don't need fractions. And then at the end, we're going to eventually have to fractions, but this avoids them and it saves a lot of time.
That's so much better than I went straight for the 1/3.
You were thinking like a computer, which you don't want to.
I guess so, yeah.
Yeah. So then I'm going to multiply. So I'm going to multiply row 3 by 2 and add it to row 2. That becomes a 0. Oops. The other -2 becomes a 0. The 1 stays a 1. This 0 becomes a 2. Any questions on that row op? Okay, I'm also
I think I found my mistake too. I think I did
arithmetic.
Yeah, it was an arithmetic.
Arithmetic will do it to you. Yeah.
Yeah, no, that's the main reason I liked calculus so much is because there wasn't as much arithmetic as.
There's definitely arithmetic in this class. There's very little hard math, and there's a whole lot of easy math, and that's what gets you. And by the way, as you get better and better at math, you don't get better arithmetic. I stopped getting better decades ago. Sorry. The basic arithmetic, at least. I'm much better at like 3-digit multiplication in my head than I used to be. But losing minus signs, I'll still do that. Okay, so I'm gonna finish because it only takes some. We're almost done. I might as well finish. I'm gonna multiply by -3, the third row, and add it to the first row. That 3 becomes a 0. This 1 becomes a -2. This 0 becomes a 3. Any questions on that? Ooh, let's hit enter. Will it let me? There we go. Okay, now I'm just gonna still gotta have fractions eventually, right? So now I gotta divide by 3 on the second row. But doesn't that make it a lot easier?
Yeah.
And dividing at the beginning. Okay, and then I think what I'm going to do is I'm just going to say it because it takes a long time to type it. The matrix inverse, the inverse is -3, 0, 3, 0, 1/3, 2/3, 1, 0, -1. Are you all okay with that?
Yes.
The last step, and that's the last step. I could type it all out, but it would take a long time. I think that's waste your time. Any questions on that? Okay. The good news is, and this is why you must show your work, especially on the exam, is that if you do everything right, but you lose a minus sign, maybe on the second step or something, and that's your exam, then I'll give you a 9 out of 10 probably. Okay, so the idea is that if you don't show your work and you have the answer wrong, you get a 0. So definitely show your work. Let's see, the -3 should be -2. Did I type something wrong? Let's see, this guy. Let's see where we are, which would mean this guy. And that one came from, yep, that should be -2. Thanks. See, like I said, I'll make arithmetic, especially when I'm typing at the same time. Boy, it's hard. How do you check your work, by the way? Let's suppose you had an extra 10 minutes on the exam. And this was an exam, so, you know, I wouldn't say your life depended on it, but you might as well try and get it all right. What would you do?
You multiply,
these,
inverse
yeah.
by A.
Yeah, you
Just
multiply the
locate the
two
identity
matrices,
matrix.
and what should you get?
I.
I. Okay, now only do this at the end, because again, you'll still get 9 out of 10 if all you did was a minus mistake. Do you see that? But, you know, if it was really important, or if you're an engineer and you're doing some kind of, you know, I don't know, road safety construction, and if you make a mistake, you kill someone, then you check your work. Okay, and you have a lot more time too. Any questions at all on this? Okay, so now we're going to give you a little exercise. Okay, so I am starting with the identity matrix. Hopefully you're all familiar now that that's the identity matrix. Okay, and I'm doing the 3 by 3. I could do 2 by 2 or 7 by 7, but 3 by 3 is not too huge, but it actually shows you some of the complications. So I think it's worth it to do 3 by 3. Okay, and 1 by 1 tells you very little. That's the problem. So I'll usually do 3 by 3 as examples, sometimes 2 by 2. Okay, and here's what I want you to do on a piece of paper. I want you to take this identity, and I want you to come up with an example of each of the following. Okay, and by the way, these are not supposed to be hard. This is not like a trick question. Okay, and if you remember, there were 3 row operation types. Do you all remember that? The first is you switched 2 rows. Another row operation type is you multiply a row by a constant. Okay, maybe I should say before I do that, not any, what do I need to add in there besides A, in between A and constant?
Non-zero.
Yeah, because if you multiply by 0, it's not a row operation. It's not allowed. Okay, and the third is you can replace a row by the sum of that row plus a multiple of another row. Okay, so I'm going to give you a couple caveats. One is I don't want you to multiply by 1 because that's boring. Do you agree? And similarly, this multiple on number 3 can't be 1 either. That's also kind of boring. It can't be 0 either. Can't be 0 or 1. Okay. And that's just for the exercise we're doing. So I want you to do number 1, do number 2, and each of these you're doing to the identity. So you're not using number 1 to do number 2. But I want you to write down a matrix, which is the identity with 2 rows switched. I want you to write down a matrix, which is the identity, which is with 1 row multiplied by a constant. And I want you to write down a matrix that is the identity with 1 row replaced by the sum of that row and a multiple of another row. And you should have 3 matrices. This is not a trick question, by the way. It's not supposed to be hard. And I want you to write it down on a piece of paper. We're going to use what you're writing. So don't do it in your head, because we're not done yet. And if there's any questions, I can help you, but I promise you this is not supposed to be hard. So I'll give you 10 more seconds. And the idea is that we're going to do a bunch of things and you're going to see what happens. And I think it's easier to remember what happens if you do it yourself than if you watch me do it. as long as I lead you through the process. So far, so good. Anyone need more time? Okay, do you agree that was easy? Okay, so the first thing is an elementary matrix. This is a big definition and really important. So an elementary matrix, E. By the way, when you think of elementary, what do you think of?
Easy.
Fundamental.
Easy, yeah. So these are easy matrices. Okay, these are easy matrix, like elementary school, right? Some of you might have had a hard time in elementary school, but mostly because you're growing up, not because of the work. But an elementary matrix E is a matrix obtained by applying a single elementary row operation to the identity. And that's called an elementary matrix. So on your paper, you should have 3 elementary matrices written down. Do you all have that?
Yes.
Okay. By the way, is the identity matrix an elementary matrix?
I think you could argue that, since you could just say, like, I multiplied by the constant 1.
Yep. The identity is an elementary matrix. How about the 0 matrix, 2 by 2 or higher, though?
No, you need multiple row identities.
Right. If it has more than 2 rows, if it has more than 1 row, then the 0 matrix is not an elementary matrix, because you just can't get there. You'd have to multiply by 0. You're not allowed to multiply by 0. Remember? That's not allowed in row operations. So the 0 matrix is not an elementary matrix. So let me give you an example. It's kind of boring, but I want to make sure you realize it doesn't have to be 2 by 2. I mean 3 by 3. So an example. Oops. Is that an elementary matrix?
Yes.
Yeah, that is an elementary matrix, because you take the 2 by 2 identity matrix and you multiply row 2 by 2. Okay. Just a note, I want to give you a nice little application. It's the one I gave you last time. Do you remember the big application I gave you last time? That was the computer gaming one. Okay, now I'm simplifying things. First thing is, we're going to assume we're going to like not change colors or opacity. So we're just going to change the way the screen sizes and rotates and stuff like that. This is an elementary matrix. And what this will do to the screen is it will expand the y coordinate by a factor of 2 and leave the x the same. Can you see that? If you multiply by xy, you end up with x and 2y. So it turns out that if you take an elementary matrix, you can look to see what it does to a 2 by 2 or what, to the world if it's 3 by 3, and it actually does stuff. And it turns out combining elementary matrices will do anything. That's the cool thing. So you can make anything happen basically as long as you stay in the number of dimensions that you started with. And you can make it happen as long as it's linear. And you learn in calculus that if things are smooth, which is true in the real world, by the way, for just about everything, right? In terms of the way things move and stuff. But you zoom in enough, everything's linear. You got that in calculus, right? Right? You got it in first quarter calculus. I guess you got it in Bruce for both of them. And then you got it in fourth quarter calculus when you're talking 3 dimensions. So these elementary matrices are also the elementary matrices of how to change the view of the world. I don't know if you've thought about that. Okay, and you can go to color scheme and stuff like that, but then all of a sudden, you're talking about very large matrices. But you can still go elementary, And every transformation that you're going to be doing on that computer screen can be done by a sequence of elementary matrices. So if you're a programmer and programming a game, you're going to be programming a sequence of elementary matrices to make the visual effect occur. Any questions on the application? Okay. Again, I don't require you guys to know computer programming, but I strongly suggest that you learn that someday if you don't know it, because it's used nowadays everywhere in STEM. So you'll want to learn that someday. Take some courses. Definitely worth it. Doesn't matter what language, actually, but just learn some programming. Okay, any questions on what an elementary matrix is? Okay, so again, it could be 2 by 2, it could be 3 by 3 as you have in your paper, it could be 100 by 100. No way am I going to draw one. But there are lots.
I have a question.
Mm-hmm.
To get an elementary matrix, do you have to start at the identity?
That's our definition.
Okay.
Now, can I get it without doing that? Yeah, because I'm familiar with it. I have them all memorized. You know what I mean? I mean, did I really start at the identity and write this out in my head? No, I know what an elementary matrix is, and I know that's one of them. Do you see? And we're going to see another way of getting an elementary matrix, but we'll see it by expiration. I promise. Got it? Okay. So now here's what I want you to do. I want you to take your elementary matrices that you have on paper. Okay. And I want you to consider this matrix. I just made up a bunch of numbers. 2, 1, 0, negative 1, 3, 5, 4, negative 2, 6. There's nothing special about matrix A, except that it's 3 by 3, so it'll actually work for your matrix. And I want you to find E times A for each of these 3 matrices. So you're going to multiply. So there's a practice in how to multiply matrices. It shouldn't be that hard, by the way. Elementary matrices are elementary, so there's going to be some zeros in them, and there'll be nice stuff. And then I want you to tell me what you notice. If you look at the multiple of E times A for each of your matrices, and you look at what you get, what's the difference between A and E times A? And think about how you got that elementary matrix too. So I want you to explore this. And I hope you can all do it. This isn't supposed to be a hard exercise, but it's supposed to be a very revealing exercise on what's going on. So there's nothing tricky here. And I'll give you a minute to do these because they are 3 by 3s, but they're not hard dot products. Hopefully you weren't evil to yourself and like multiplied by 0.53276 on your example. that'd be stupid. Hopefully you had nice numbers. No reason to be masochistic.
I see it.
All right, let's give everyone else about 30 more seconds because this is really important. Okay, let's start with the first row operation. Switch two rows. So you got an elementary matrix by switching two rows in the first part of the exercise. And then you multiplied that matrix by times A. And what happened when you multiplied times A?
I switched the two rows.
Exactly. Did everyone see that? Just want to make sure that you're all on board here. So if you do the row operation to the identity and multiply that matrix that you get by A, then you're doing the row operation to A, at least for switching two rows. Did everyone get the same thing? I'm not hearing everyone.
Yes.
Oh, good.
Yeah.
Okay, now let's look at the second one, make sure that we're not like dreaming about anything. Okay, we multiplied a row by a constant and got an elementary elementary matrix that corresponded to multiply row by constant. We multiplied that matrix, let's call that E2, by A. And what did it do to A?
It multiplied the same row by the same constant.
It multiplied that row by a constant. Isn't that nice? Okay, and then the third one, if you replaced a row of the identity with the sum of the row plus a multiple of another row and got an elementary matrix, call it E3. Take that E3 and multiply it by A, what happens? If you did everything right. So what's the result? Everyone's being quiet? Is it because you don't know or because you're not there yet or because you're shy?
I'm just shy.
Just shy. Okay, well, hopefully you notice that when you did that, what you're really doing is you're doing the row operation to A. Anyone notice that? It's the same as replacing a row of A by a multiple of a different row plus that row. And it's the same replacement as what you did to the identity. So this is a major, major, piece that we can use. So one thing, and again, I always throw computer programming in there because that's today's world. This allows us to do row operations in a much nicer way with programming. Computers can handle multiply one of the rows by a number. That's really easy. Quick little for statement on A of I, where I is the row number. Okay, it's really simple. Trust me on that if you don't know programming. Similarly, on the others, you can do that also. So it's very easy to program a computer to do row operations. Okay, very simple. Okay, if you know how to program a computer. If you don't, then it's very difficult because you got to learn how to program them first. That's hard. Any questions on this example? It's not even an example of this exploration. Okay. So now what I can do is I can take what we learned and we can write it down. And there's a theorem. It says, let E be an elementary matrix corresponding to a row operation. Then E times A is the matrix that is obtained by performing that elementary row operation on A. Any questions on the theorem? How would you prove this theorem?
What we just did.
Yeah. You'd literally have 3 steps. Maybe I'll do the first step. maybe I'll do the first step. And the problem is kind of a pain, is that there's a lot of symbols you have to write. So let's go proof. I'm not going to prove all 3 steps because it'll take a long time. Proof 1, and that means, well, the first row operation, switching 2 rows. Okay, and what we can do is we need to say what is EA. I need to make this a equation. What is EA sub, oops, parenthesis, EA sub IJ? Huh? Oh, it's doing all kinds of bad stuff. Didn't like the parenthesis. There we go. Okay. All right, well, how do you get EAIJ?
You dot EA.
Okay, right, we're gonna take the ith row with the jth column of A, right? All right, well, what's going on here? Well, first thing, if we're looking at E, so we've now switched 2 rows. So if neither of these the I and J there we go. Doesn't like lowercase I but as a single, wants a capital, and J were switched. Then the row, then what's going on here? So that means we're just talking about the identity. Remember, the identity doesn't change anything. Do you remember that? So that's not gonna, that's just gonna be AIJ. So then we get AIJ. Because again, that's just multiplied by the identity, and you haven't changed. If you haven't changed the identity, if you haven't changed that row of the identity, then it doesn't matter. Is that clear? Okay. And in fact, not even neither. It's really if I hadn't been switched. It's not J. J is a column of A, and that's not important. It's the ith row that matters. So if I was not switched, so lowercase I won't let me do it. There we go. Okay, then you just get AIJ, nothing changed, and that's what you expect, because that means if you're not on that row, then it better not have been switched. Does that make sense? Now, what if you are on that row? So if I is one of the switched rows, then what happens? Then AIJ is the same as your A, except something's going on here. And what's going on here is we switch the E rows. And what does that do? That means the 1 got moved. Does that make sense? then the 1 in the identity is moved from the ith component to the jth component. But if it's moved from the ith component to the jth component and you dot them, that means you're keeping the jth element of the column. Not jth, ith to the kth, because we're switching I and k. J is the column. Then the result is no longer aij, but akj. So copy and paste. Element. And that's what we need to show. Because when you dot a vector that's all zeros except 1, and that 1 is a 1, then what you're doing is you are keeping the entry of the second vector where the 1 was. So if you move the 1, then we've changed which one we're keeping. So instead of keeping the ith one, we're keeping the kth one. So that says we're switching I and k. So that's the ith and kth rows are switched. One thing you're going to learn about linear algebra proofs, they're usually paragraphs. Get used to it. It's not like calculus proofs where most of it is just one equation after another equation after another equation. These are words and sentences. So it takes a while to get used to it. It's the hardest part about this whole class, to get used to how to write sentences to describe what's going on. Okay, again, I don't have time to prove the other two, but they're kind of similar ideas. Any questions at all on the theorem and the proof? This is a scary part, right?
I have a question for you.
Uh-huh.
Can you do the same thing we just did with systems of equations?
Well, you could do it with homogeneous systems because matrices are homogeneous systems.
Okay.
You could do it with systems that aren't homogeneous, but it's not that helpful.
Okay.
Yeah. I mean, you do it with a matrix. You don't do it with the system. See, the first step is to turn it into a matrix. So the answer is, can you do it with matrices? Absolutely. That's what this is. Do you see that? So the whole point is you never have to deal with systems with X's and Y's and stuff ever again. It's much easier to do with matrices, whether you're writing it on paper or whether you're programming a computer. It's a lot less writing once it gets complex. Do you believe me on that?
Yes, I do.
So there's no reason to stick around with systems. That's like holding on what you're used to, even though it's harder. And a lot of people do that, but you want to move to matrices because they're easier in so many ways. Okay. If it's a 2 by 2, then it probably doesn't matter because it's all easy. But as soon as you leave 2 by 2, matrices are the way to go. And if you don't believe me, I'll give you a 5 by 5, and I'll tell you, you try to do it with a system. Good luck. Okay, but with matrices, you can do it. A little messy. You can write a program and make it happen easily. Okay, any other questions on this before I move on? All right, next thing for you to do. I bet you didn't expect you're going to do a whole lot of things. But the next thing is, for each of your elementary matrices, find the inverse of that elementary matrix. And I promise you it won't be that hard. So it'll be interesting. Especially the first one. The first one's interesting, and the second one is not going to be the same idea as the first one. Just a warning. Same way of solving it. The first one shouldn't take more than 10 seconds. The second one shouldn't take more than 10. The third one might take a minute, a little bit longer, but not much, maybe 30 seconds. And you can let me know when you're done. And if the inverse doesn't exist, you can write that down, but I will tell you, you should worry if you end up writing that down. So let me know when you're done.
I just finished.
Anyone else finished? I don't want to waste your time, but I don't want to, hustle you through it when you're not done yet.
I think I finished.
Okay.
Yeah, I think I'm there.
Did you? Okay, so let's start with the first elementary. Let's the switching two rows. So that was E1, I call it. When you take the inverse, what'd you get?
Same thing.
E1. Okay. So it should make a lot of sense because remember that matrices are functions, and an inverse is doing the function backwards, right? So if you switch two rows backwards, what are you doing?
Switching two rows backwards.
You're switching the same two rows. The way you unswitch two rows is you switch those rows again, right? Okay, so you should get the same thing for E1. Okay, E2, you won't get the same thing, but what'd you notice?
It was the reciprocal.
You multiplied the
Of my
same row
constant.
by the reciprocal, right?
Yeah.
Okay, which makes sense because if you take a row and multiply by a number and you want to undo what you just did, what do? You take that row and multiply that by the reciprocal. Is that clear? And I'm not sure if you can see it from your matrix, but when you do the third one, the E3, and you find its inverse, that's undoing what, but multiplying a row by a constant and adding it to another row and replacing. I don't know if you can see that in your matrix, but that's what's happening.
So I think a good way to do it, to see it, is I multiplied it by a -2,
Mm-hmm.
and now it's positive.
Yep, that'll do. Yep. Okay, so you can definitely see that. So the main thing, so there's a couple things. One is that all of these elementary matrices are invertible, but they're not just invertible. The inverse of an elementary matrix is an elementary matrix. Okay, so now there's some theorems, some really important ones. Okay, so the first one is if E is invertible, okay, so that's what we just found, at least with your examples. But it's not hard to just take your, when switching two rows, it didn't matter which rows you switched. Do you agree? That's going to work on all of them. Multiply by a constant. Instead of, if you had the constant 4 or something, just call it A and it'll work, non-zero constant. And you'll get 1 over 8 times that row, and that's your inverse. So it's pretty easy. The proof is you just stick in letters instead of numbers. Okay. So then E inverse is a matrix that corresponds to applying the row operation in reverse. Because E applies a row operation, E inverse is undoing the row operation. Do you see that? Very important. Okay, so the proof is kind of, that's it. I mean, that's the whole proof. Okay. So what that says, one thing is that all elementary row operations as matrices, elementary matrices, are invertible. And you can actually see what they do. Okay. I also want to remind you that if you have two invertible matrices and you multiply them, then the product is invertible. Remember that? That we had that on Monday. So if A and B are invertible, then A times B is invertible. Okay, so that brings us up to the next theorem, which is an important one. Let's suppose A is an M by N matrix, and B is RREF of A. Okay. Then B is equal to U times A, where U is a product of elementary matrices. Why is that true? Why is that immediate? Do you remember how you do RREF?
Row ops.
Row ops. Okay, so you apply a row op. Okay, so let's suppose you applied a row op E1. Okay, well, you apply a row op now by multiplying by matrix. Does that make sense? So we're going to have A, and then we're going to do E1A, and then you do another row op, right? And that'll be E2 times E1A. Because every time you do a row op, you're multiplying matrix. And then you do it again and again and again, and eventually you RREF. That's what RREF is. Do you agree? And you end up with EN through E2, E1, A. Any questions on the idea there? This is the proof, by the way. This uses what we've already done. Okay, but then we could do the following. We can use a big theorem that we had a couple days ago and realize the associativity property of matrices. You can write it like that. Put the parentheses wherever you want. Remember that a couple days ago? one of the properties of matrices. You can do, you know, you can't switch the order, but you can switch the parentheses around. Any questions on that? And there's our proof. We just found a product of elementary matrices times A, and you got RREF of A. Because that's how you do RREF, is you do one elementary matrix at a time. Any questions on that? Okay, so we can find, you can find B by using the same steps as you found A inverse if you want to. By the way, that'll always work. Okay, so in other words, you augment A with the identity, you RREF, and the right-hand side will be B. So there's nothing new here except the question. Before the question was find A inverse, right? Now the question is find B. So B will be, let's see, by the B, oh, I'm sorry, it should be the left-hand side. That's an error. B will be the left-hand side. So if A is invertible, the left-hand side is the identity. If A is not invertible, the left-hand side is not the identity. Any questions on that? Anyone lost? Okay, and it's busy work. Again, this is, you just do it. But there's a step-by-step process. And we'll see how much time we have to do some of these. But it just means that if you want to find your RREF of A, you augment it with the identity, and then you RREF, and that gives you your thing. Okay.
So B is not A inverse, correct?
Let's see, BUA. Oh, you know what? Sorry, it was right. B is not A inverse. B will. So here's the big thing. So B is U times A, right? So B is the RREF of A. So if A is invertible, B is the identity. Do you see that?
Yeah.
But if A is not invertible, B might have a row of zeros on the bottom. So B is the RREF of A. So that's why, sorry, so that's why I wrote left-hand side. That was my mistake. The right-hand side is going to be your U. And that's kind of how this works.
Okay, I got it now. Thank you.
Okay, so here's a lemma. And I don't think I've ever said this word to you guys. I don't know if Bruce has. And this is not a citrus fruit that's pretty sour. It's lemma. Hey, do you guys know what that word means, lemma? It's a math word. It's not.
Honestly, I don't remember the difference between lemma and corollary.
They're kind of opposites, actually. So lemma is a smaller idea theorem that helps you prove a bigger theorem. And corollary comes after the theorem. So corollary is a theorem that is a result of another theorem. So they're almost opposite. So the lemma helps you prove a theorem, the big theorem, and a corollary is a theorem that comes from the big theorem. Do you see the difference?
So a lemma is kind of like a sub-theorem, sort of?
It's a helper theorem. I like to use it that
Okay.
way. It's a helper theorem. So it gets you what you need to be able to prove the big theorem. And that's not a linear algebra word, that's a math word. But you may not, but again, this is your, maybe your first like proofs class. Sound right? Although geometry is often a proofs class, at least. I don't know if it's still, I think they've gotten rid of that in high school.
I think it was when I was still in high school. So
Yeah, they're kind of getting rid of the proofs. which is sad. Okay, so here's a lemma. If A times B is the identity, okay, first thing, does that mean that A and B are inverses of each other?
Yes.
One more guess.
No.
No, because for them to be inverses, you also have to have B times A as the identity.
So they both have to be true.
Yeah, they both have to be the identity. AB and BA both have to be the identity.
Okay.
Okay, but AB equals the identity could happen. They might be inverses, they may not be. But if they are, if AB is the identity, then RREF of A does not have a row of zeros. Why is that true?
If there's a row of zeros, then it might eliminate one of the ones that like corresponding to whatever row it's in.
Right,
Row.
right.
Okay.
So we always, if A has a row of zeros, let's say it's the third row, then AB will have its third row also be a row of zeros because of the dot product. Because you take that row and you dot it, and each time you dot it, you always get zero because zero dot anything is zero. Do you remember that in last quarter? Okay.
Yeah.
So the proof is by contradiction. If A has a row of zeros, then the ith row of AB is all zero, is a zero vector. By definition of multiplication, right? Because every column dotted with that row is always zero. So you can have a bunch of zeros as you go across. Okay. So, but that can't be true because the identity doesn't have a row of zeros. So that's contradiction. Since I does not have a row of zeros. Any questions on that lemma? It's an easy proof. And notice you don't need to have equations. This is just explaining it out, logic. Any questions on the lemma at all before I go to the next lemma? Okay, the next lemma is if A, let A be an M by N matrix such that A times B is the identity, then M must be less than or equal to N. Why is that true?
If it's greater than n, then it's likely there's going to be a row of zeros, which would eliminate the possibility of an identity.
If it's greater than N, doesn't that necessarily have a row of zeros? How about A being all ones? That doesn't have a row of zeros. Could be 1, 1, 1, 1, 1, 1. 3 rows. Okay, so it's not that A has to have a row of zeros, but here's a hint. Look at the lemma above it. Okay, we know AB is the identity. Therefore, RREF of A does not have a row of zeros. Is that clear from the prior lemma? So A may not have any rows of zeros. That's fine. But then RREF of A does not have a row of zeros. Do you agree? From the prior lemma. Okay, but if M is greater than N, that means there's more rows than columns. then then you can't have more than n pivots. Do you remember that? Then the number of pivots is less than the number of rows. So what do you know about the last row of our REF? The pivots go in order, right? But if you run out, then what must the last row be?
Zeros.
Yeah, a row without pivots. A row of RREF of A without a pivot must be a row of zeros. Any questions on that? And that's the proof. So that's a contradiction because you can't have a row of zeros from the prior lemma. Any questions on the lemma? Okay, here comes a nice, easy theorem given the two lemmas. If A is invertible, then A is square. Why is that true? Based on the lemmas.
M is equal to N.
Right, but we were hoping so. That's what we're trying to prove.
Mm.
So here's the deal. If M is greater than N, then A can't be invertible by the prior lemma. Is that clear? Because there can't be, right? Because remember, if RREF of A has a row of zeros, that's not good. Then you don't have the identity, right? You're not going to find an A times B as the identity. You have to have A times B as the identity to be to be invertible. Okay, but that's if M is greater than N. What if M is less than N? Any idea what we can do? Any thoughts? Then look at A transpose. Well, A transpose then has more rows than columns. If A had more columns than rows, because remember, transpose switches the idea of column and row. Then by the lemma, the transpose of A is not invertible, but we had a theorem before that said that the inverse of A is the inverse of A transpose is the transpose of the inverse of A. Remember, you could switch inverse and transpose, but there's a contradiction. Since if A is invertible, we have a formula. For the inverse of the transpose of A. But if you have a formula for the inverse of the transpose of A is invertible, right? If you know how to find it, then it exists. So therefore, A is square. Any questions on this theorem? I guess what I didn't do, one word, proof. Forgot to write proof. And here, proof. I think it wants a comma. Yeah, it wants a comma. Any questions at all on this big theorem? All right, next theorem. A lot of theorems today. If A is square, then RREF of A is either the identity or it has a row of zeros. Okay. So why is that true? See if anyone can tell me. I think I'm going to say this one because it's simple.
Because if it's a square, then the RREF, I don't really know how to explain it that well, but the RREF basically means that there's going to be a pivot in every row with zeros above and below it. And if it's a square, then that means it will be the identity because every row will have a pivot in it, and they'll be moving in a diagonal pattern.
It could have a pivot. So there's two cases. The first case is A is invertible, right?
Yeah.
So if A is invertible, then RREF of A must be the identity. That's part of being invertible, right? Is that clear?
Yeah.
If A is not invertible, right? That's obviously the only other possible case, right? Then why must you have a row of zeros? And that's what you were saying. Because you look at the pivots, that means that you don't have a pivot in every row. So that means that last row must have been all zeros.
Yeah.
Any questions on that theorem if I don't write it out? Is that right?
So it's basically just a toss up. It's either going to be an identity or it's not.
Right, but in particular, it's either identity or not identity. That you can say about any matrix, right?
Mm-hmm.
Right. Everything in the world is either this or it's not this, right? As long as this is well defined. Right.
I have a more general question. How long do you think it takes to sort of ingrain this sort of proof speak into your, I don't know, how long do you think it should take to be able to explain a proof in words?
It all depends on the person.
Okay.
But I will tell you, this is hard. Okay, it's not hard to listen to me, but it's really hard to come up with the words yourself. And there's really only one way to get good at it, and it's not to listen to me. Do you know what the only way to get good at it is?
To do it ourselves.
Yeah, to practice. If you don't practice, it's not going to happen. You may understand every single word I say, and that doesn't mean you can write it down by yourself, come up with it. So it's hard for me to teach it because even if you feel comfortable with what I'm saying, doesn't mean you've got it.
I sort of get how the proof functions, before you explain it, in this case, in this specific case, but I just don't know how to really say it properly.
Yeah, and that takes practice. Just takes a lot of practice. One thing I recommend strongly is after you've written it down, say it aloud, read it out loud to yourself and make sure it makes sense.
Okay.
And if it doesn't make sense, then it's not okay. Okay, especially if it doesn't make sense to you and you wrote it. So that's always important, is to read it out loud and make sure that what you just said made sense.
Okay.
I know that sounds obvious, but not everyone does it. Okay. All right. Now comes the big theorem of the quarter. And this is the TFAE theorem. Notice I put it in, do you know what I didn't do? Let's do it. There. It's that important. We need to make it big. This is the theorem, and it is the following are equivalent, TFAE. Okay. Number one, A is invertible. Number two is RREF of A is equal to the identity. Okay, we're going to be adding to this list. Okay, how long do you think the list will get?
Pretty long.
Probably around 40.
Holy.
Yeah, just let you know, this is the big concept of the entire class. But we're not there yet. We're on 1 and 2. So I'm leaving space, a lot of space. And again, it all depends on how much detail you put in. You know, there's a lot of different details. So 40 is you put in like just about all the little things that could happen. And then if you put only the major one, it's more like 15.
Is this like the fundamental theorem of calculus for this class?
Well, the fundamental theorem of calculus doesn't grow. You just use it every day.
And you find different ways to apply it.
Yeah, this one just keeps growing.
Okay.
Yeah.
So it's even more important than the fundamental theorem of calculus, basically.
Yeah, it'd be kind of like if I asked you, what's another way in another language to say hello? Can you tell me?
What was the question?
What's another way in a different language, not English, to say hello?
Gracias.
Good, good. No, gracias isn't true. That's not hello. That's
Hola?
thank you. Yeah, if you want Spanish, it's hola.
Hola. That's
Hola,
right.
right? Hola. Okay, but are there others?
Yeah.
Yeah, a ton.
Absolutely. Yeah, there's shalom, for example. That's Hebrew. There's, I don't know, konnichiwa. That's Japanese. How many of them are there?
Ni hao, it's Chinese.
Thousands.
Ni hao,
Mandarin.
exactly. Yeah, this is kind of like that. Is that every time you learn a new language, you have another word for hello. Well, every time we're going to learn a new concept in linear algebra, we're going to have another word for invertible. Does that make sense? Yeah, bonjour. There's a lot of hellos, by the way. Okay, and I don't pretend to know all of them. I probably know 5 or 6. Okay, but the point is, there's a lot of words that mean invertible, but they're not just words, they're true ideas. And one is RREF of A is the identity, and we just proved that. And do you know what it means to be equivalent? If you had to prove that these are equivalent, what do you have to prove?
That they mean the same thing.
Yeah, but what are the steps?
They equal the same thing?
What's that
Not
mean? Then?
necessarily each other, but the same thing.
But what are the steps in the proof? Step 1 is?
Find the inverse of A and then find the RREF of A.
No, we're doing a proof because we don't have an A. This is just for any A. Good luck, doing it for every possible A, by numbers. Okay, so let me tell you. Step 1 is assume A is invertible. And then you need to prove or deduce that RREF is the identity. Step 2 is assume RREF of A is the identity. And then we have to conclude or prove that A is invertible. Do you see the difference in those two things?
Yeah, you start with 1, and then the second case you start with 2. And then you
right. Now, if there were 3 of them, what would we have to do?
Start with 1, 2, and 3, and then equate it to 1, 2, and 2, and go on in that fashion.
Maybe what you're thinking is right, but what you're saying isn't quite. You start with 1. You assume 1 is true, prove true is true. Then you assume 2 is true, prove 3 is true. Then you assume 3 is true, prove 1 is true, and that's what you need to do. So you need to go in order, and then when you get to the bottom, you need to get back to the first.
What happens if our initial assumption is wrong?
What do you mean?
Like, suppose we were trying to prove something, and I wanted to assume that A is invertible when it's not.
Okay, so you're saying assume A is invertible, period. You're done. There's no it. There's no example A. We're saying let A be an invertible matrix. You're declaring it. And when you're declaring something, there's no such thing as it could be wrong. You've declared.
Okay. I get
Does that
it.
make sense?
All right.
And if you declare it's invertible, that means it must be true that RREF of A is the identity. Do you see? And vice versa, if you declare A is not invertible, it must be true that RREF of A is not the identity. Does that make total sense? Okay, so this theorem I already proved. That was just above it. Did you notice that? So if A is invertible, then AB is the identity. That's the definition, right? You can always use the definition. And if AB is the identity, then RREF of A is the identity, because that's what we just proved. Up here somewhere. Did I prove it? Let's see. Yeah. So if A is square, RREF of A is either the identity or it has rows of 0, right? But if it has a row of zeros, then it's not invertible. So that gives it to you. Do you see that? So that means it must be the identity. So this is the following or equivalent theorem. You need to get this one down. And again, we're going to be adding to it all the time. Any questions on that? Okay, so I have a little time left. And what I thought I'll do, since whenever I have a little time left, I'm going to let you choose. Let me go new share. That one. And let me do, is it that one? Yeah, but I got to go here. Pick a number between 42 and 60 that's not one of these. You can say it or type it in the box. You choose. $51. Okay, 51 it is. So let's go grab it. Okay, show that ABC inverse equals C inverse, B inverse, A inverse by verifying that when you multiply, it works. Okay, so let's do it. So we want to verify these guys. So ABC all inverse. So now let me go back. I think I need it as an equation. Just a minute. Okay, so we need to show ABC inverse is equal to A inverse, B inverse, sorry, backwards, C inverse, B inverse, and times C inverse. Okay, and we use a definition. We know that you have an inverse if when you multiply, you better get the identity. Is that clear? So let's do that. So I'm going to take ABC. See if it lets me. And I'm going to multiply that by C inverse. I guess I should put parentheses. Ah. What the hell? B inverse. Oh, that should be an A, not a C, the last one. A inverse. Okay. Now what can I do first? Let's see, I'll jump in.
Wouldn't it be I?
That's what we're hoping for. But we have to get there.
Mm-hmm.
You have to talk about which property you're using. Let's use the associative property, which means I can switch around the parentheses. Does that make sense? So that's equal to AB. I'm going to write it without parentheses and stick the parentheses in because Word doesn't let me put parentheses in. AB, C, C inverse times B inverse A inverse and now I'm going to put the parentheses here and here. And I guess here and here. Okay, now what can I do? What's C times C inverse?
I.
That's I. That I know because I know that C times C inverse is I because that's what C inverse means. So now I can take what I had and I can take that C inverse and I can turn that into an I, which is good. Now what I can do is I can take what I had and I can adjust the parenthesis however I want. And there's a few choices. I'm going to do it this way. What's B times I?
B.
B. Good. So B times I is B. Now I could take this. I don't know if you see what's kind of happening. And how can I adjust the parentheses now?
We can group A and A inverse and B inverse.
Not the A and A inverse. They're outside each other, but the B and B inverse can be grouped.
Okay.
Remember, you can't switch the order of things. You can only change parentheses. Switching the order is not allowed in matrix multiplication. Do you remember that? But you are allowed to change the parentheses. But what's B inverse? B inverse.
It's I again.
Yep. So I can take that B inverse and turn it into an I, and we're almost there. So now I can take the parenthesis, go like that. And what's A times I? Yeah, A times I is A. And now what's A times A inverse?
I.
And that's I. I'm halfway done. Why am I only halfway done? You don't remember because I need to show it both ways. Now we're out of time, but basically you do exactly the same thing as I just did. So now we need to have the C inverse, B inverse, A inverse times ABC and end up with I. And basically you switch the parentheses, you multiply by the matrix times its inverse, get the identity, multiply the identity, drop the identity, and then just keep going. It's exactly the same. Any questions on this proof? We're out of time, so I'm going to stop share. And I'm also going to stop the recording, but hopefully this made sense.